Hello everyone, I welcome you all in this session. As we have discussed some of the examples of the vector space in the last video, let's discuss some more examples here. For example, we will discuss the vector space R3 over R with the usual addition and usual multiplication. First, we will check what is the structure of R3. As you know, its elements will be x1, x2 and x3 if there is any element x. So these xi's are the real numbers. Now we just prove that this is a vector space. So here the v is our r3 and our field f is our r. So going to the vector addition properties. So in the vector addition, first if we have the two elements of the r3, so that's our v. So then in the internal composition we are considering the first operation, that's here plus, then x plus y, that is x1, x2, x3, and y has the coordinates, for example y1, y2 and y3. And if you will see, it is x1 plus y1, x2 plus y2 and x3 plus y3. So it is again in the R3 because x1, y1 are the real numbers. Sum of two real number is again a real number. This is again a real number. This is again a real number. So it is the element of R3. Now going to the second property, that is associative property. So for the associative property, you are taking the three elements. Let's say we have x, y and z from the R3. You have to prove that x plus y plus z, so that is equal to x plus y plus z. So here you will get x1 plus y1, x2 plus y2, x3 plus y3, and your z is z1, z2, z3, and here on the RHS you will get x1, x2, x3, and plus your y and z, that is y1 plus z1, y2 plus z2 and y3 plus z3. So it will be equal to x1 plus first coordinate, adding with the first coordinate, so y1 plus z1, x2, y2, z2, x3, y3, z3, and on the RHS first coordinate with the first coordinate, so x1 plus y1 plus z1, second x2 plus y2 plus z2, and similarly x3 plus y3 plus z3. So it is associative as well. Going forward, so now the third property, the identity you have to check, that is the zero of the vector space. That means you have one element in your R3 such that if you will add it to any x, you will get the x itself. Your x is here, it has the three coordinates x1, x2, x3. You have to add some vector from the R3 such that you will get x1, x2, x3. So as it's very obvious that you will add 0, 0, 0 and 0, 0, 0 is the element in the R3. So we got that element. So this is called the zero of this vector space. And the fourth property is the inverse, that is you have one element from your R3 such that if you will add it with the element you will get the 0, so that is 0, 0, 0. So here the element is x1, x2, x3. You have to add one element such that you will get 0, 0, 0. So you will add minus x1, minus x2, minus x3. So if this is x, so that vector will be minus x. So minus x is again the element of R3. Similarly, you have to prove that x plus y is equal to y plus x. So what is x plus y here? x1 plus y1, x2 plus y2, x3 plus y3. Since this is a real number, it is commutative. So I can write it y1 plus x1 y2 plus x2, y3 plus x3. So it is nothing by plus x. Now next to 5 external properties, external composition, so that we call as a scalar multiplication. In the scalar multiplication, our property, that's the sixth property, take any element of the field. What is the field here? You know the field is R, so take any real number alpha and take any a vector. So from the R3 you have to check alpha, the second composition, second operation, that's multiplication, alpha times x, that is alpha times x1, x2, x3. You have to multiply it, you will get alpha x1, alpha x2, alpha x3. This is a real number. Multiplication of two real numbers is a real number. Multiplication of two real numbers is a real number. Multiplication of the two real number is real number. So it will be in R3 as well. Okay, seventh property is that take the two elements alpha and beta from the R and one element from the R2, then alpha plus beta times x. Okay, so that is alpha plus beta times x1, x2, x3. That is alpha plus beta of x1, alpha plus beta of x2, alpha plus beta of x3. It is equal to alpha x1 plus beta x1, alpha x2 beta x2, alpha x3 beta x3. It is nothing alpha x1, alpha x2, alpha x3 plus beta x1, beta x2, beta x3. So it means it is alpha x1, x2, x3 plus beta x1, x2, x3, that is alpha x plus beta x. So you have proved this property. Okay, now our eighth property, take the two vectors, let's say one scalar from R and two vectors from your R3. So you have to prove alpha times x plus y is alpha x plus alpha y. So what's that? Alpha, you know, x plus y will be x1 plus y1, x2 plus y2, x3 plus y3. It is equal to alpha x1 plus y1, alpha x2 plus y2, alpha x3 plus y3. It is equal to alpha x1 plus alpha y1, alpha x2 plus alpha y2, alpha x3 plus alpha y3. So it is nothing, it is alpha x1, alpha x2, alpha x3 plus alpha y1, alpha y2, alpha y3. That is nothing alpha x1, x2, x3 plus alpha y1, y2, y3. That's nothing alpha x plus alpha y. That's our eighth property. The ninth property is same. Alpha, beta are from the R and alpha x is any vector from your R3. Alpha times beta times x will be alpha beta x1, x2, x3. That is equal to alpha beta x1, alpha beta x2, alpha beta x3. That is alpha beta x1, beta x2, beta x3. That is alpha of beta x. Similarly, you will take beta of alpha x. Okay, so now the last property is that you have one element from your R such that that element multiplied with the element x belongs to R3, so should be your x only. So what is that element? You have to multiply a scalar with x1, x2, x3 such that you will get x1, x2, x3. You know that scalar will get multiplied with every coordinate, so you will say it is 1. And what is a real number? So it means that all the properties hold. So R3 over R, comma, with first addition and multiplication is a vector space. Okay, so now it's the homework for you. You will prove that Rn over R plus multiplication is a vector space. Is a vector space. So what is Rn? I will define it here. The Rn is nothing. It is R, so on, R how many times? N times. So you know what is the element here. So it is a set. If X is any element in this, it has n coordinates. Let's say x1, x2, so on up to xn. Okay, so these xi's are from the R. So this is the vector space as well. Okay, let's now discuss another example, that is C over R. C is a complex number, so with usual addition and multiplication. Okay, you know the elements in the C complex set is the element, for example x, it will have the representation a plus iota b, where a and b are the real numbers. Okay, so now our field V is C and our field here is R. Okay, so now let's take the vector addition. So in the vector addition, first we have the closure property. Okay, so that is, take any two elements from the C and add them x plus y. So that is, if x is equal to a plus iota b, y is equal to c plus iota d, then x plus y will be a plus c, sum of the real part, okay, plus iota b plus d, imaginary part. This is the sum of two real number. Sum of two real number is again a real number, so it will be again a complex number, so it is closed. Second is associative. Take x, y, z are any three elements of C, then x plus y plus z is equal to x plus y plus z. I hope everyone can do this. Just take x is equal to a1 plus iota b1, y is equal to a2 plus iota b2, and z is equal to a3 plus iota b3. So here what you will get from this LHS, you will get a1 plus a2 plus iota b1 plus b2, then add with the z, that is your a3 plus iota b3 should be equal to, now your x is a1 plus iota b1 plus y plus z is a2 plus a3 and plus iota b2 plus b3. Now if you will solve it, this is the real part, this is the real part, so a1 plus a2 plus a3, this is the imaginary part, this is the imaginary part, so iota b1 plus b2 plus b3. On the RHS, this is your real part and this is your real part, so a1 plus a2 plus a3 plus iota b1 plus b2 plus b3. So LHS is equal to RHS, so it is associative. Okay, now we have to find the identity. So take any element of this complex number such that if you will add it to any complex number, you will get the same complex number. So your complex number will be a plus iota b. You have to add some complex number to get the same a plus iota b. What's that? 0 plus 0 iota, that is your 0. So 0 is the complex number of the 0 vector. Okay, now what is the fourth property? Take any complex number such that if you will add it to any of the complex number x, you will get the 0 plus 0 iota. So if x is a plus iota b, what you have to add to get the 0 plus 0 iota? So you know a plus iota b, if you will add with the minus a minus iota b, that is you will get the 0, because a minus a plus iota b minus b, you will get 0 plus iota, so that is minus x. Fifth property, x plus y. If x is a plus a1 plus iota b1 and your y is a2 plus iota b2, then the addition will be a1 plus a2 plus iota b1 plus b2. a1 a2 are the real numbers, so you can take it as a2 plus a1 because real numbers are commutative, so plus iota b2 plus b1, so it is same to say it is y plus x. Okay, now take the scalar multiplication, that is called the external composition. In the external composition, we are taking the second operation, multiplication. Let's do that. So what is the sixth property? Take any element of the field, and your field is here R, is it? So your field is here R. So take any element of the R and take any element of the C, then multiply alpha with x. So here it will be equal to alpha, your x is A plus iota B, so that is alpha times A plus iota alpha times B. This alpha is a real number, A is a real number. Multiplication of two real numbers is a real number. Multiplication of the two real numbers is a real number. It is again in the representation of a complex number. So alpha A plus iota alpha B. Okay, seventh one, take any two real numbers and any vector from the C. Now alpha plus beta, multiply it with this x. So it will be alpha beta, is it? Alpha plus beta into A plus iota B. So that is alpha plus beta times A plus iota B, or alpha plus beta times B. So that is alpha A plus beta A plus iota alpha B plus iota beta B. Now take alpha A and alpha this, so you will get alpha common, A plus iota B. Now plus take this one and this one, so you will take the beta common, you will get A plus iota B. A plus iota B is your x, so it is alpha x plus beta x. Now the eighth property, take one real number and the two complex numbers, so then alpha times x plus y. So that is alpha x plus y is A plus A1 plus iota B1 plus A2 plus iota B2. So it is alpha times A1 plus A2 plus iota B1 plus B2. That is alpha A1 plus A2 plus iota alpha times B1 plus B2. That is alpha A1 plus alpha A2 plus iota alpha B1 plus iota alpha B2. Now take this one and this one and just combine it. What you will get? Alpha common, A1 plus iota B1 plus take this one and this one. So what you will get? You will get A2 plus iota B2 when you will take alpha common. So it is alpha, this is your x, plus alpha, this is your y. So you got alpha x plus alpha y. Okay, now the ninth property, take alpha, beta, any real numbers, and x is any complex number. Then alpha times beta times x will be alpha beta A plus iota B, that is alpha beta A plus iota alpha beta B. So these are complex numbers, so you can take alpha common, so that is beta A plus iota beta B. So you can say alpha beta of x. And the 10th property, you have some real number from R such that if you will multiply it to the complex number, you will get the complex number. Is there any such a number in the real number? So this should be the real number which you will multiply with A plus iota B such that you will get the A plus iota B. You know that number will get multiplied with A first, then with this one first. Okay, secondly, so what is that number? 1. So 1 is a real number, so the unit is here 1. It means that complex number on the field R with the first addition operation and usual addition and usual multiplication is a vector space. Okay, remember here, if f is any field, if f is any field, for example your q, r or c, then f over f with addition and multiplication is always a matrix space, always a vector space. So here even fn over f usual addition here these are the operations which you will use in the field is also always vector space, like q over q addition multiplication, r over r addition multiplication, c over c addition multiplication. Similarly r n over r, q n over q, c n over c. Okay, these are the vector spaces, always the vector spaces. Now I will say is r over c a vector space? As I already discussed it in the previous lecture, previous video, here the complex number, that is the field, is the superset of the real number, so it cannot be the vector space. Okay, so thank you very much. In the next lecture we will discuss the vector space, that is mn over r and the set of polynomials. Thank you very much.